Okay, welcome back. And we are again live on this National Science Day program live from the Inter-University Center for Astronomy and Astrophysics here in Pune. All of you join us every year on this particular day, and we have thousands of visitors, 10,000s in fact. And we are very thankful to all the viewers who've been joining since morning, and we have kind of achieved that mark. We see that there are 10,000 viewers in the first session today. So that's an amazing achievement, and we definitely want to have a lot of programs happening. So the promise that we will be doing a lot of events henceforth online, and so that you can get more information, we bring to you the next session. Of course, before you get into that, don't forget to subscribe to our channel, because that's how you'll keep getting notifications about all the happenings in the coming week. Definitely, there are going to be lots of exciting programs from IUCAA SciPop. So, सोनल, आप कुछ हमारे व्यूअर्स को बता दीजिए।
जी हाँ, तो आप सभी का वापस एक बार स्वागत है हमारी पब्लिक टॉक की जो सेशन है। तो उनमें हम आगे सुनने जा रहे हैं कुछ जाने माने वैज्ञानिकों से कि नोबेल प्राइज जो 2020 में मिला था ब्लैक होल्स के बारे में, तो उसके बारे में हमें जानकारी मिलने वाली है अगले सेशंस में। लेकिन उससे पहले मैं फिर से एक बार आप सभी को ये रिमाइंड करना चाहूँगी कि हमारे चैनल को ज़रूर सब्सक्राइब कीजिएगा। और हमें ये कहने में बहुत खुशी हो रही है कि जैसे हमने देखा कि IUCAA के कैंपस को हर साल 10,000 लोग कम से कम विजिट करते हैं, यहाँ पे आते हैं। आज भी हमारे शुरुआती सेशन से लेके अब तक 10,000 से ज़्यादा लोग विजिट कर चुके हैं। तो we are very happy to convey this message that and to see that all people are really excited to learn from scientists, and National Science Day is actually getting celebrated on wide range. Thank you.
So we are close to the time of the special talks that we have every year, and we choose the very relevant topic of the previous year's Nobel Prize, particularly in physics. In some years, we've also covered other subjects, chemistry, biology, etc. But this year, of course, the Physics Nobel Prize of 2020, which was announced, went to astrophysics. So we had to make a good event of that. And so without further ado, we bring to you and introduce to you the three scientists, all of whom actually in a way work with black holes. So they are specialists in that. And so while the talk will, the main talk series, both of them will start at 5:30 to 5:30. I thought we should have a small chat over tea amongst these three scientists whose work is about black holes. So they're here having tea with you, and please take the floor away, Professor Shomak Rai Chaudhary, Professor Sudipta and Sarkar, Professor Sudipta Sarkar, and Professor Dipankar Bhattacharya here live on IUCAA SciPop channel. Welcome, everyone.
Thanks, Amit, and thanks, Sonal. I'm very happy that normally in the last few years on the National Science Day, I was just looking out and looking at what our courtyard looks like and the science park looks like on a National Science Day, and I'm feeling really sad that I don't see anybody there. And then I think about those 10,000 people who would have visited us, actually have watched us on the web. And the great thing is that this will be there on YouTube, and a lot of people will actually watch it in the days and weeks to come, which is quite reassuring. This year, as you say, is very special that the Nobel Prize in Physics was given to astrophysics. Now, traditionally, there is this notion that Nobel Prizes don't come to astrophysics, because, as you know, when the Nobel Prize was started at the beginning of the 20th century, hey, there's an echo coming from somewhere. From the will of Alfred Nobel, it seemed that he had written down that it has to be given for applicable physics. And so from the very beginning, the prize was given to experimental subjects, experimental achievements. So much so that even when the prize was given to Albert Einstein in 1924, it was given to him not for his towering achievement of the general theory of relativity, but was given for discovery of the photoelectric effect, which is used in many gadgets, or interpretation of the photoelectric effect. So later on, of course, this has changed because a lot of theoreticians have got the Nobel Prize, particularly in physics. I think this all started in the early 70s with Martin Ryle and Tony Hewish getting the Nobel Prize for the discovery of quasars and pulsars. Then the cosmic microwave background has got Nobel Prize, the discovery, Penzias and Wilson, and later on the Kobe experiment, Mather and Smoot. Then Halson Taylor got the Nobel Prize for the binary pulsar and tests of general relativity. Giacconi got the Nobel Prize for X-ray satellites, X-ray astronomy. But even then, it was all to do with experiments, building things. Chandrasekhar and Fowler were the first people, I think, who got the prize in theory, in astrophysical theory. And then later on, we saw amazing prizes given to the dark energy discovery and the LIGO discovery of gravitational waves 4 years ago, by the LIGO collaboration. And then we had last year Peebles and Mayor and Quilos being given the prize for cosmology. And so we're very happy that, and extrasolar planets, and this year as well, Nobel Prize. So astrophysics is gaining a lot of popularity. I wanted to ask the two panelists today, I mean, what do they think? Were you surprised that astrophysics has become a subject of fashion now in the Nobel Prize?
I think so. I mean, back-to-back 2 years in astrophysics is very surprising.
Yeah.
But
you're getting used to atomic physics and condensed matter physics.
Yes,
like
absolutely. Because since last year also there was astrophysics prize, and we didn't really expect that another astrophysics prize will follow so soon. Although the discovery has been spectacular. I mean, there's no question that this deserve a prize. But the question is, how often do you get these prizes?
But I mean, discoveries sometimes in theory or in observation take decades. Chandrasekhar made his interpretation in the 1930s, got the prize in 1984. So, but then sometimes it happens very fast. So dark energy, for example, people were surprised how fast that happened.
Yeah.
And LIGO, it happened in 1 or 2 years. So that's the thing. Are things open to interpretation? The other aspect of this is that Indians, even though directly an Indian has not got a Nobel Prize for astrophysics yet, but they have been involved in a great way in the work leading up to these discoveries. The LIGO discovery is a good example in which, even though 3 people got the Nobel Prize, the 1,000 people who were in that in the discovery paper, out of that 40 were Indian scientists working in India. Similarly, in the black holes work this year, there's some very interesting and important Indian names who contributed to that work. Sudipta, right? Can you talk about, for example, the Indian contribution to this work?
Absolutely. I think traditionally the Indians have contributed significantly in the theory of relativity, general relativity. We all know the first translation of the Einstein's paper from German to English is done by Saha and Bose in Calcutta. I mean, that is probably only few years after the final theory of...
No, it was in the same year, 1915.
Yeah. So they actually understood the theory, which is probably one of the greatest achievements of human thinking at that time, and then translated it back. Similarly, there is great achievement and contribution by P.C. Vaidya in the form of Vaidya's solution of black holes. And then particularly Amal Kumar Raichaudhuri of Presidency College, the Raichaudhuri equation, which played I would say, crucial role in proving this theorems, which Hawking and Penrose later proved, which is like bedrock of our understanding for black holes. So it's actually this year Nobel Prize, particularly the Penrose's part, is very interesting because it relates fundamental physics and astrophysics. The black holes are interesting thing for both people working in high energy theory as well as astrophysics. But the fact that we can now detect such object with such a high accuracy, the observational techniques and data analysis is such powerful now. really exciting that we are living in great era.
I think that will also feature in this. I mean, the technological achievement that that had to be done before the black holes were characterized. I think that will be highlighted today. That is also themselves, the adaptive optics, the infrared observations, all that's very important. And also the amount of technological advancement that has happened in numerical work on general relativity as well as exact solutions that has led to all this stuff is also extremely important. The Indian connections are also very interesting to all these people. For example, Penrose has been to India many, many times. Of course, we've seen him here in IUCAA several times and has a very strong connection with Indian scientists. Andrea Ghez, who is one of the discoverers of the orbits around the central black hole, has been with us in the TMT project because she's one of the major people involved with the TMT. So we've had some very close connections, and so this is why we, from the Indian perspective, are looking at this prize as even more important than it normally is. So I think we've reached the time of the advertised time for the talks. I propose that we start with there are two talks that are coming now, and on this year's Nobel Prize. This Nobel Prize was given to Roger Penrose, half the Nobel Prize for theoretical work done on black holes and the observational work done on the supermassive black hole in the middle of our galaxy, given to Andrea Ghez and Reinhard Genzel. So we start with the theory talk. Is that all right? With the talk on Roger Penrose with Professor Sudipta Sarkar. So let's start with that. And so Sudipta is associate professor at IIT Gandhinagar, and do you have your thing? Okay. So let me just say a couple of things about him. He of course did his PhD here in IUCAA a long time ago, more than 10 years ago. And then he went off to the University of Maryland as a postdoctoral fellow, came back to IMSC Chennai, worked for a little while in ISER Mohali, and has been on the faculty of IIT Gandhinagar from about 2014. So he's going to talk about the one half of the Nobel Prize, at least this year, which is to do with the theoretical work on black holes that have been. So Sudipta, take it away.
Thanks a lot. I think I'm audible, right, Shoma?
Yes, yes.
Great. So thanks a lot, Shoma, and I'm very grateful for IUCAA for giving me this opportunity to present this work. Of course, the last year Nobel Prize was really exciting for all of us working in the field. And it is quite interesting that in a same year, the theory and the observation has been provided the prize. And this shows that the future of science is going to be extraordinary, okay? And for young minds, this is probably the time to venture into astrophysics. So with this advertisement, let me start my talk. So as you can see that the Nobel Prize pictures of these three people who got this Nobel Prize is there. And also the famous picture of the center of our galaxy, the Sagittarius A, which is supposed to be a supermassive black hole. That picture also you can see at the extra wavelength. So what I'm going to talk about, I'm going to describe the theoretical side of the black hole physics, particularly I'll concentrate on work by Roger Penrose, and then the rest of the part, particularly the observational side, will be covered by Dipankar in the next talk. So let me start. So this is the citation of the Physics Nobel Prize 2020. The half of the Nobel Prize is given to Sir Roger Penrose, and the rest half is divided to five equal parts into Genzel and Andrea Ghez. And if you look at the citations are quite interesting. If you see that for Roger Penrose, the citation says, for the discovery that black hole formation is a robust prediction of the general theory of relativity. And for the other part, the citation says, for the discovery of supermassive compact object at the center of the galaxy. Interestingly, the second citation doesn't mention black hole, and there are technical reasons for it. But it is clear that this prize is a celebration of the concept called black hole, which is around, it is there with the physicist idea for the time of maybe more than 50 years, starting with John Archibald Wheeler coining the term. So the recognition of this result is actually the combined work of many physicists. So starting with Albert Einstein to many, many physicists, theoretical physicists, observational physicists, astrophysicists, astronomers, all of them combining ultimately led to the verification of this remarkable result. And the story of a black hole is a remarkable testimony of the power of human thought. And it's actually, there are very few such examples in history of history of science, that a theoretical idea which originated from complicated mathematical equation later become part of our reality. Okay? And this is really exciting, that we can think of ideas completely mathematical, completely abstract theoretical idea. It turns out such ideas are there in the nature. So this is, I find personally, quite interesting. And these are the part of the reality now, and these are various pictures which you are going to see in the talk, which suggest the existence of black hole. And nobody is more happy than this discovery, I'm sure. Albert Einstein obviously looks happy in this picture. So let's start. So the story of the black hole, I mean, basically even it predates relativity theory. In fact, if you look at the history of science, there is a very interesting letter written by English philosopher John Michell, which is who was also a great physicist as well as an experimentalist. So who wrote this letter where he talked about objects which are very compact, so that the escape velocity of any object on the top of those stars or planets is greater than the speed of light. And if that happens, nothing can escape that planet. So let's see, the formula for escape velocity from your school physics is, you know that it's given by this formula, and it means that escape velocity increases if you decrease the radius of for a given mass. So you start with this planet. So this planet has some mass, and somehow there is a giant which collapses this planet, keeping the mass constant into smaller and smaller radius. What you immediately see is that the escape velocity increases. So it takes more speed to escape the gravitational pull of that planet. Great. So let's ask this question. This is the exact question John Michell asked, that given a mass m, what should be the radius so that the escape velocity is equal to the speed of light? And we all know what is the speed of light is 3 into 10 to the power 8 meter per second. So you solve this equation for the radius given the mass for which the escape velocity is equal to the speed of light. Good. And then what will happen for such bodies if their escape velocity is more than the speed of light? That means even light will not be able to escape from that planet. The gravitational pull will take the light, bring it back to the planet's surface. So you can't see it. In fact, let's call this star is a dark star. And if you take sun, which has this mass of 10 to the power 30 kg, and currently the radius of this, and if you think of what is this radius, if I want to make sun as a dark star, it will turn out it will be roughly 10 kilometers. And what it means is that if you take the sun and collapse it to 10 kilometers, 10 kilometers will be like roughly the size of our IIT Gandhinagar campus, or a little bit more than that, okay? And so if you collapse the star to this small entire sun to this 10 kilometer size, okay, think of how dense that object will be. Then what you have done is that you have made sun a dark star. Fortunately, that is not possible, okay? I mean, we can't really collapse the sun to 10 kilometers. It's not that easy, okay? In fact, there is a movie called Dark Star I found in IMDb, and if you wish, you can see it. So the question is, interestingly, in the John Michel's idea, that there is a light which is affected by gravitational pull. Remember, in those times, light used to be thought like a corpuscle with certain masses. Okay, so different frequencies are corresponding to different masses. This was the Newtonian corpuscle theory of light. So in that view, it is easy to comprehend how light is affected by gravity. And in Newtonian idea, gravity is a force. So this is this famous Newtonian law of force, gravitational force law, Gmm by d square, which all we have studied in our school days. So as Newton has taught us, the gravity is a universal attractive force which acts on massive objects instantaneously. Okay, but light is a wave. The Newtonian corpuscle theory of light turns out to be wrong, and then there are many experiments. For example, this famous picture of diffraction grating it shows that light is a wave. So it's not very clear that how a wave, and ultimately we know that light is an electromagnetic wave, it is not clear how a wave will be attracted or influenced by the gravity. At least in Newtonian gravity, it's not a very well-defined question. So therefore, John Mitchell's idea of black star or the dark star remained only an obscure academic curiosity. Great. Here comes at the beginning of the 20th century or the end of the 19th century. If you look at the history of science, at that time, science was dictated by two pillars. One of them is led by Maxwell, and these are Maxwell's equations. What does this Maxwell's equation do? So these equations describe the properties of electric and magnetic field. So they tells us, given the charges and currents, what are the properties in electric and magnetic fields over. On the other hand, there is this Newton's laws and Newton's laws of gravity, which tells us what is the mechanics. So mathematically, every phenomenon in nature in 19th century was thought to be either electromagnetic phenomenon described by the laws of electrodynamics, the Maxwell's equation, this four Maxwell's equation, or mechanical or gravitational, which can be described by Newton's laws of physics. So this is like the pillar of classical physics. Okay. And it turns out nature is not that simple. And there comes this wonder here, 1905, where there's a clerk in the Swiss patent office. He led a revolution which changed the way we look at our universe. And this is the story of Albert Einstein, who developed the theory of special relativity in 1905 and proved and proposed a new theory, a new mechanics, which replaced the Newton's theory, Newtonian mechanics, and which is consistent with the Maxwell's theory of light. So what Einstein did is that he changed the Newtonian mechanics, introduced a completely new paradigm shifting ideas, and it turns out there are experiments at that time and when now also which offer conclusive support in favor of this new theory. And the crucial concept in the special theory of relativity was and is that nothing can move faster than the speed of light in vacuum. There is a fundamental speed limit in this universe. Whatever you do, how much energy you spend, you cannot move faster than the speed of light in vacuum. That's all. Okay, Newton's has changed, the Einsteins have changed the Newtonian mechanics, but what about the law of gravity? Can we make Einstein's theory of special relativity consistent with the Newtonian gravity? And then turns out the answer is no. Not only that, this kind of questions led Einstein to a far greater achievement. And this is what we call the theory of general relativity. Einstein started thinking about general relativity immediately after the discovery of special relativity, and particularly after 1907 when he discovered something called equivalence principle. But it took him almost 10 years to write down the theory in its final form. Okay. So what is this theory of general relativity? In one sentence, theory of general relativity is a relativistic theory of gravity. Newton's theory of gravity was not consistent with Einstein's theory of special relativity. General relativity is basically a theory of gravity consistent with special relativity. But the consequence of relativity into gravity is remarkable. It turns out, in Einsteinian picture, gravity is no longer a force. It has become a property of the space-time around a massive body. Not only that, it turns out gravity affects the causal structure, the flow of time, and most importantly, the motion of light. So the question, which was not very clear in Newtonian picture, how light is affected by gravity, is actually very elegantly solved in Einsteinian picture, where Einstein actually gave us equations, how exactly we should write down the motion of light around massive objects like sun. So for example, one of the experimental verification of general relativity is the bending of light, of starlight, when it comes near the sun towards us. And there is a very famous experiment done by British physicist Arthur Eddington, which verified this bending of light, and there are modern experiments also. This is a famous picture of gravitational lensing by a galactic cluster, a massive collection of galaxies, and this kind of picture shows the gravitational lensing of light because of the massive gravity of these clusters, the collection of huge galaxies. So Einstein gave us the instrument the mathematical calculation, the mathematical law by which we can calculate how light is affected by gravity. That is clear now. Great. So what is general relativity? As I told you, in general relativity, the gravity is no longer a force. It becomes the geometry of the space-time surrounding a massive object. And in fact, the Einstein equations of general relativity basically is a relativistic generalization of the Newton's law of gravity, relates properties of geometry with the properties of matter like energy and momentum. Okay. Of course, I'm not going to explain these Einstein's equations. You are welcome to any GR class, but this is actually beautiful. Believe me, when physicists look at this equation, they do see beauty in it. I mean, I really cannot explain why I feel it beautiful in non-technical terms, but a day-to-day physicist actually feels that why this equation is so remarkable, so elegant. So one side of equation is matter and energy. The other side equation is geometry. The geometry, which is, described by Gauss, Neumann, Riemannian geometry, many great mathematicians have described this properties of this geometry. What Einstein did is that he related this geometry with the matter content through one equation. He related geometry with physics. So this is a remarkable achievement. Now it turns out mathematically this equation is remarkably complicated. For if you talk to a mathematician, this equation is a coupled partial differential equation, hyperbolic nonlinear partial differential equation. Whatever those words means, they are actually means they're very, very difficult to solve. In fact, they're very difficult to solve even in a computer. Okay. So therefore, there is a separate subject called numerical relativity, which is devoted in solving these equations, understanding the numerical solutions of this equation. Okay. Now, what it turns out that though it's difficult, there are very, very simple, elegant, and remarkable solution of Einstein's equation, and those was known even at the beginning days of general relativity. For example, physicists are known for this bad approximation. They always start with what is called a spherical set system. Okay, systems which looks like a sphere. Nothing is spherical in our world, but spherical systems are good approximation of certain real world system, and they're easier when you can solve the mathematics easily. So if you look at the sun, in one approximation it looks like sphere. Okay, of course it's not a real sphere. It has irregularities. That's like sun. Earth is not a real sphere, but up to a certain extent we can assume at least that it is a sphere. What physicists, the mathematician and relativist at the beginning days tried to solve Einstein's equation outside a spherical body. That's like the simplest case possible. And this is German professor who is also a famous astrophysicist at that time called Schwarzschild solved this problem, and he actually solved this problem while fighting in the First World War. This is remarkable. He was probably in the trenches and where all the fighting was going on, and he was solving Einstein's equation on a paper. Okay? You can think of the romanticism involved. And this is a picture of Schwarzschild, and this is probably one of the representative picture of First World War. What is actually Schwarzschild did? So what is solved is the notion of gravitational field outside a spherical body. So if you talk to somebody like Newton, he will say, okay, the force, there is a gravitational force which is related by this formula. What Schwarzschild gives is a relativistic generalization of Newtonian gravitational force. Of course, the actual mathematics is written in terms of something called space-time metric. Let us not worry about it, but you can see, even if you look at it, it looks so different. Basically, what this second equation does is that it describes the space-time surrounding the body. Okay. So this is what is called the famous Schwarzschild solution. Even if you are not interested about details of this solution, look at it, that when you are looking at one of the terms, particularly the second term, the denominator, that diverges for a particular value of the radius. Okay. Now, anything which diverges, believe me, is a really bad thing. Okay. So there must be something going on, funny things going on at either r equal to 0, where also all these things diverges, and also that particular value of radius for which the denominator of the second term is 0. So this is the radius, which is 2gm by c square, and if you remember my first few slides, this is exactly the radius of a dark star, John Mitchell's dark star of mass n. So it turns out, even in the relativistic theory of gravity, which we call the general theory of relativity, there is something interesting happening when a body of mass m has a radius lower than this radius, and this radius has a name, we call it Schwarzschild radius. If you actually analyze this Schwarzschild solution mathematically, it turns out that this at the radius, so when body collapses and out of its own gravity and slowly become smaller than the Schwarzschild radius, an event horizon forms around the body. What does it mean is that you can, this event horizon is a one-way membrane. You can enter into the event horizon, but you cannot come back. This is like this famous lakes of this one California, okay, if you know that song. So you can, when the body collapses and ultimately becomes smaller than the event horizon, then it becomes what we call a black hole. This name is coined by the famous gravitational physicist John Archibald Wheeler. And the Schwarzschild radius of Sun is 10 kilometers. Again, what it means is that you need to completely compress the Sun to 10 kilometers so that the event horizon forms outside that. Less than the 10 kilometers, event horizon forms at the 10 kilometers, and then it becomes a black hole. You can go into that hole, but you can never come back. Of course, remember what is important, that this is different from John Michell dark star. Because in John Michell dark star, there is a naive way of understanding how light is affected by gravity. So what you are thinking is that there is a gravitational force which is pulling the light, bringing it back on the surface. Just like it will bring anything you throw, it will ultimately fall down on the surface. That is not what is happening here. Here, things are quite subtle. Here, the structure of space-time itself is such that you cannot cross the event horizon in one direction. You can only cross it, go into, but you cannot come out. Excellent. So we call this object, this mathematical object, to be a relativistic dark star. But again, there is absolutely no guarantee that such dark stars are actually there in nature. Because to create this dark star, you have to compress the entire Sun into 10 kilometers or less. So it seems it is probably an academic curiosity. Or you may ask this question, are there such objects in nature? So first question is that what is that force? How can such enormous objects like Sun or massive star, how can they collapse into itself and form something like a black hole? The answer started to come beginning with the great work by Subramanian Chandrasekhar, the theory of stellar collapse. What Subramanian Chandrasekhar shown that the stars produces energy using nuclear fission. This was known before, converting hydrogen into helium and many other complicated processes. But there is a critical mass, and we call that mass, today we call it Chandrasekhar mass or the Chandrasekhar limit. The idea is that stars with mass less than this Chandrasekhar limit exhaust their hydrogen at the end of the nuclear fusion, and they can become a stable system called a white dwarf. And if you look at the brightest star in the sky, which is the Sirius, okay, and it turns out the Sirius is actually not a single star. There is also a companion star, small companion which you cannot see by naked eye, and that is called the Sirius B. And it turns out that's actually white dwarf, the stable star, okay, and because its mass to begin with was less than the Chandrasekhar limit. But what happens if the stars whose mass are far more higher than the Chandrasekhar limit? It turns out there is another critical value, and for that case, the stars collapses and ultimately forms what is called a neutron star. So these stars, the gravitational inward pull are protected or opposed by something called a quantum degeneration pressure, which arises from the basic quantum mechanical physics. But basically the neutron star is actually gets stable by the neutron degeneration pressure, just a white dwarf is stable by what is called an electron degeneration pressure. Now you may say, okay, there are more massive stars in the sky. What happens to them? And this is what turns out, and it was shown that such stars, there is absolutely no force which can stop the collapse. The collapse will continue, and then the question is, what is the end state of this collapse? Interestingly, there is one of the beginning papers of gravitational collapse came from Calcutta University from a person called B. Dutt. He analyzed the problem even as early as 1938, in those days, okay? And ultimately, Oppenheimer, Dutch, Heidegger, collapse, they analyzed this problem and they have shown the end stage of gravitational collapse, if we assume a spherically symmetric system, most probably, even if you assume pressures and other things, complicated things, most probably a black hole, okay, where there is a formation of the event horizon. So this idea that there is a natural process of the creation of black hole is very exciting. And at the same time, there are great observational results related to quasars. The massive explosions in the sky led to a renewed interest. And it turns out there is a possibility that this mathematical object called black hole are actually realized in nature. And therefore, all over the world, theoretical physicists, mathematicians tried to understand the properties of black hole, the mathematical properties of black holes in much more greater detail. This happened during the time of 60s and 70s, and it has even given a name. Nowadays we call it is to be the golden age of relativity research. So let's go ahead with this. Every black hole solution in general relativity, whenever mathematicians try to understand them and look at their properties, turns out exhibits a bizarre thing. The center of the black hole at r equal to 0, remember? It turns out things goes completely ill-defined. What happens at r equal to 0 is that it turns out the density of the collapsing object somehow becomes infinite. The measure of the gravitational force, something called curvatures, okay, it turns out they're infinite. The tidal forces which can deform objects, it turns out near the center, the tidal forces become very large and reaches infinity. And this is the center we call the singularity. Okay? The singularity is the center of the black hole where things are infinite. And therefore, the mathematical structure of spacetime itself is not very well defined. The existence of singularity, this infinity, says that we cannot do calculations anymore. It is as if the general relativity itself predicting its own downfall. It's very interesting, and one of the example of this is not very, proper example, but you can think of the Rutherford atom. Okay. The Rutherford atom itself saying that it is not a stable system, because if the electron, a charged particle, moves around proton, it will radiate, and the system will collapse, and the time scale of this collapse is very small, so therefore the atoms cannot be a stable system. But we do see surrounding us stable atoms. So there must be something wrong in the classical idea of atom. Exactly similar thing you can think of, that at the center of a black hole there is a singularity. Things goes infinity. So there must be something wrong in the theory of general relativity. It cannot be applied at the center of the black hole. Okay. In fact, now it is widely believed that quantum theory will make this singularity vanish. Something called quantum gravity, which we still not understood properly. So every black hole solution which mathematician could solve turns out to have two crucial features: event horizon and singularity. A one-way membrane, you can enter into it, you cannot come back, and at the center, a world of infinities, we call it singularity. So basically, the next question we can ask that, okay, all these singularities we have found, are they very generic? Why? Because look, you have solved this Einstein's equation only for spherical symmetry. You have assumed your sun to be spherical, your black hole to be spherical. You have assumed collapse to be spherical. Is that a problem with your idealization? Whether gravitational collapse of massive star always lead to singularities? Is it just we cannot solve it for complicated system, but real world is actually complicated? It's a problem for approximation. And also the important question, whenever the singularities come, whether they are accompanied by the event horizon. So these are important questions which needs to be understood. Otherwise, this theory is too ideal, this mathematics is too ideal to apply to the real astrophysical problems. I give an example where there is the ideal infinity, but in real world there is no infinity. And this is from school physics. All of you know the notion of resonance. When you apply a periodic force to a system, and the frequency of the applied periodic force becomes equal or close to the natural frequency of the system. There's a famous incident, an infamous incident rather, of soldiers marching on a bridge. And when the natural frequency of the bridge, when the marching frequency becomes equal to that, the bridge starts shaking vigorously, and at the end of the day, bridge can actually collapse. Good. So this amplitude, it turns out to be, if you do calculation, is infinite in magnitude. Okay? It turns out, if you just do the calculation, the answer is infinity. But that cannot be. How can the amplitude is infinite? And if you plot it, particularly if you look at this dotted line, there it seems that at the resonance, when the frequency of the periodic vibration is exactly equal to that in frequency, amplitude is infinite. But it turns out such infinity is very unphysical. That is because in real world there will always be some damping force, like friction. And whenever there is a friction, all this colored graph shows the amplitude at the resonance is no longer infinity. So it could possible that black hole singularity goes away when you consider real physical world, when all the dirtiness of the astrophysical system, gases, deformities, okay. Is it that the case? The answer turns out to be no. And this answer is given by the Roger Penrose by a remarkable mathematical action. What he did is analyzing Einstein's equation, proved amazing mathematical theorems using remarkable mathematical techniques, showing that singularity is the generic prediction of general relativity. General relativity always has singularities at the center of the black hole, irrespective of however complicated the system may be. It may not have spherical symmetry, it may have very, very crazy form of matter, but singularities are there. And this is the famous paper by Roger Penrose. This is the Nobel winning paper, and it's published in Physical Review Letters, and you can see the underline, what I have underlined myself, which says that he's asking simply a property. The question has been raised whether this singularity is in fact simply a property of the high symmetry edge. And he gave an answer that no, it is not the result of the symmetry, but rather a mathematical consequence. Penrose proved conclusively that singularities are the generic feature of the gravitational collapse, provided certain reasonable conditions are satisfied. These conditions are mathematical. I'm not going to talk about this condition, but they are very reasonable. For example, one of the conditions says if energy is positive. Some of the conditions says if causality is maintained. This looks okay, at least in our classical world, and as a result, the singularities are inhabitable. It turns out these theorems are one of the greatest results of mathematical physics. And it turns out this proof requires very new, what's called topological techniques. Okay. These are mathematical techniques which physicists were not at all aware of. So Penrose actually taught other physicists how to use these mathematical techniques to prove results, which was quite difficult to prove. The physical significance of this theorem is remarkable. What they proved, that Einstein's theory of general relativity cannot be the ultimate theory of nature. It's a classical theory. It requires new ideas. The predictability of physics demands that the quantum theory, there must be a quantum theory of gravity, and we must get rid of this singularity. These singularity theorems are later generalized by Hawking and Penrose, and there's a book by Hawking and Ellis which actually summarizes this result. And today we call them Hawking-Penrose singularity theorems. This singularity theorem asserts that at the center of every black hole and at the beginning of the universe, there must be a space-time singularity. And that the space-time singularity, the classical general relativity, breaks down. And here is a photo of Stephen Hawking with Roger Penrose, one of the greatest physicists of our time. And these theorems begged, and they gave us a challenge to the contemporary physicists to solve the problem of singularity. It's a challenge to us that classical general relativity cannot be used at the center of black holes. There are problems of infinity. Can you solve them? So you can understand the power and the consequence of this theorem. I should also mention that the singularity theorem requires a very crucial input. It came from Professor Amul Kumar Raychaudhuri, who used to work in Presidency College. Professor Raychaudhuri gave a beautiful equation, and this equation is known as the Raychaudhuri equation. And this is this equation which ultimately helped Roger Penrose to solve the problem of singularity, showing that how generic the singularities are. There is still question, what about the horizon? I shown you that singularities are generic. Whether the horizons are generic? In fact, Penrose gave a new conjecture called the cosmic censorship conjecture. I'm not going to talk more detail about it. It basically says that whenever there is a singularity, they will be clothed under an event horizon. And the picture is this, there is a singularity, there will be always an event horizon outside. The research work by Roger Penrose, Hawking, and many others led to a robust classical theory of black hole. The formation of a black hole by gravitational collapse of massive stars is a well-established theory in contemporary physics. And then the detection of this system, for example, not only massive stars, now it is believed that the center of our galaxy is a black hole, is a remarkable achievement to verify this black hole paradigm. And check the next semester by Professor Dipankar Bhattacharya, who is going to talk about this amazing observation. Thank you.
Thank you very much, Sudipta. That was a wonderful talk, and I'm glad you highlighted the Indian contribution that led to the fantastic theory. In fact, it's very interesting that when I went to Oxford as a student, I attended a whole course by Roger Penrose. And in the very first class, he asked me whether I was related to Amal Kumar Raichaudhuri because my surname is the same. Because at that time, they were thinking a lot about the Raichaudhuri equation and Hawking as well. So let's move on to the next part, the second half of the Nobel Prize. And this is a talk by Professor Dipankar Bhattacharya on the other half of the Nobel Prize. And then Professor Dipankar Bhattacharya, first, is a distinguished professor here at IUCAA. He's the Dean of Academic Affairs. And he's been here at IUCAA as a senior professor for a long time. Before this, he was at the Raman Institute. And long before that, he did his PhD at the JAP program. And at the Raman Institute, and then he was several years in Amsterdam before being a professor at Raman Institute. But he has been at IUCAA for a long time. So over to you to talk about how to weigh a black hole.
Hello. I hope I'm audible.
Yes, you are.
Thank you. So this has been a wonderful year for black hole astrophysics. The Nobel Prize, and you would have also seen the Event Horizon Telescope results, the images that made covers of almost every...
That's a future Nobel Prize, isn't it?
That's a future Nobel Prize in waiting. So the observing black holes was something which was considered very, very difficult and esoteric. But over a few decades, this has become a fantastic opportunity to test physics at extreme scales. Now let us look at the Nobel Prize winning discovery of this year. The discovery is about the presence of a black hole at the center of our Milky Way. This is a panoramic view of our Milky Way, 360-degree panoramic view of the Milky Way. And at the center of it resides a black hole which is 4 million times more massive than our sun. And this is basically the result which has been awarded the Nobel Prize. How do we know this is the case? So in this talk, I'm going to take you through the developments that happened over many years, the requirements that were posed by this very challenging experiment, which has eventually led to this establishment of the existence of black hole at the center of our galaxy. The two laureates are Andrea Ghez, who shares 1/4 of the Nobel Prize, and Reinhard Genzel, also 1/4 of the Nobel Prize, the other half going to Roger Penrose, as you have just heard. And the citation just states that this is for the discovery of a supermassive compact object at the center of our galaxy. You notice that it doesn't say the discovery of a supermassive black hole, but it is a compact object. It's so compact, in fact, that the possibility of any other form of matter seems very remote. So how do you know that there is a black hole somewhere? So if you take a close-up picture of a black hole, this is how it is going to look like. Yes, you don't see anything, of course, because black hole is not luminous. It doesn't produce any light. Any light that goes towards it gets captured, doesn't escape it. So therefore, by itself, there is no way that you can image a black hole. So let's say there is a black hole somewhere here in space. Its presence is revealed only by its gravitational influence. So orbits of bodies revolving around a black hole can reveal its mass. And if there is gas surrounding it and falling into the black hole, in the process of this accretion, the gas can get very hot because it falling into a deep gravitational potential well. It is releasing that gravitational energy. Gas molecules and gas particles are colliding with each other, getting hot. And such a hot gas can radiate. And this radiating gas is the signature that, for example, Event Horizon Telescope has imaged around the black hole at the center of one of the nearby galaxies. It's not our galaxy, M87. And the signature of the event horizon is very clearly visible in this image. So black holes at centers of galaxies is not a new idea. It's been expected for many years, particularly from the existence of active galaxies. Here is an example of it's a radio image of an active galaxy. It's called Cygnus A. There is a highly powerful nucleus, and this nucleus produces very powerful jets from it. So these jets travel millions of light years, interact with the diffuse medium around it, intergalactic medium, and then produce these huge plumes which produce a very large amount of radiation. And it is believed that the power to send these jets out and create these plumes come from black holes at the centers of the galaxies. So such active galaxies include, they're known by various names like blazars, quasars, Seyferts, and so on and so forth. And they're all supposed to be powered by accreting supermassive black hole at their centers. And the Event Horizon Telescope image of M87 actually establishes this, because you can see that there is a dark object, massive object at the center within the event horizon. So the question people have asked, does Milky Way have one such black hole at the center too? Milky Way is not an active galaxy like this one. But over time, people have come to realize that even though a galaxy may not be active at a given point of time, the black hole may still exist. When you feed the black hole with large amount of matter, the galaxy becomes active and produces this highly powerful jets and bright nuclear emission. So do we have a black hole at the center of our galaxy? So the hunt for a black hole at the galactic center has therefore been an enterprise which has now spanned almost 4 decades. So what we need to know, what is the mass which is concentrated at the center of our galaxy? And if this mass is confined within an event horizon, then we can definitely say that there is a black hole there. The horizon radius, as Sudipta has mentioned to you earlier, is given by 2 times the gravitational constant g times mass of the object divided by speed of light squared. This is an expression for Schwarzschild black hole, for slowly rotating black hole. If the black hole rotates much faster, then the horizon radius can be a little smaller as well, but it is of this order. How much is it? It is 3 kilometers for one solar mass. If we want to compress the Earth into a black hole, we'll have to squeeze it within a 9 millimeter of radius. So, as we are talking about 4 million solar mass at the center of our galaxy, the horizon radius for it would be 12 million kilometers. So the question is this 4 million solar mass confined within 12 million kilometers? So that is the quest that people have been on. So the task is A, measure the mass at the center of our galaxy, and 2, measure the size within which the mass is confined. So, as I said, the presence of a black hole is revealed by its gravitational influence. And this influence would also be on anything that orbits it. So if you have a star, let us say, orbiting the black hole, then one can measure various parameters of this orbit. For example, its semi-major axis, which is A here, the period, how long it takes to go around the massive center once. That's the orbital period. At any given point of time, you can also measure its orbital speed and the distance from the center of the orbit or the focus of the orbit. So from these measurements, one can use Kepler's law to find the included mass. The included mass m, if you have semi-major axis A, or and if you have a measurement of the orbital period p, using these two measurements, you can infer what is the included mass, even if you don't see the object which is providing this mass. From orbital speed, v as a function of r being the distance from the central mass. So if you measure r and if you measure v for various positions in the orbit, then you can fit an orbital function with gm and a as parameter, and you can measure again the mass and the semi-major axis. So even if you don't fully trace the orbit, if you only have partial orbit but have measurement of orbital speed at various points, then you can use this law to measure the mass which is included. Now, if you see a star moving in the sky and describing such an orbit, remember what we see in the sky is a projection in the plane of the sky, the projection perpendicular to a line of sight. But there is also a component of this motion which is along our line of sight, which you cannot see in the plane of the sky. To really measure the mass contained within, you need to measure both the projected component and the radial component. So this requires high precision astrometry, that is position as a function of time, as well as spectroscopy, which is the study of the spectrum of the star and how it changes as a function of time. So let's describe that a little bit more. So in astrometry, we are measuring transverse motion. So let's say the star is at this point at a given time, and then we keep following it over time. It may move to another point, and so on with time. If we have sufficiently large number of measurements, then one can fit an orbit through these points and describe the orbit as projected in the sky. Now, the galactic center is located 25,000 light years away. So we're not talking about something which is just next door to us. So to be able to do precision astrometry, to infer the mass which is contained well within the center, requires very high angular resolution. The position measurement of this kind will be required to be accurate to about milli-arc second, 1,000th of an arc second. So that is like measuring a cricket ball on the moon sitting on Earth. So that is how precise this measurement has to be. To measure the radial component, one makes use of spectroscopy. And this is a well-known phenomenon in spectroscopy. If a body emits a certain spectral line, which is a sinusoidal wave, it gives you a monochromatic spectral line over here. If such a body happens to be moving towards us, then the waves get a little closer together, so the wavelength reduces. And if the body moves further away from us, the waves get stretched and the wavelength increases. So this is called a blue shift, this is called a red shift. The shift of the wavelength from its rest position is then a measure of the motion in the radial direction. So this is a Doppler shift, where the shift of the wavelength delta lambda in units of its original rest wavelength gives us the radial component of the velocity, vrad, in units of the speed of light. So if we have both astrometry and spectroscopy together, then we can really measure the 3D shape of this orbit, and then can put a constraint on the mass that is included within. So that is what is required to proceed with this measurement. Now, I said the milli-arc second resolution is required. So let us talk a little bit about angular resolution. Typically, our instruments are telescopes where we have a curved mirror, which is put on a mount, and there is a detector which collects the radiation from this mirror. And let's say a wavelength lambda is incident upon this telescope, and then we make an image using this detector. And let's say the size of this telescope, the diameter, is d. The smallest measurable angle using such an arrangement is the ratio of the wavelength to diameter. So to get the highest possible angular resolution, one really needs to use the largest possible diameter of telescopes. So the world's largest telescopes are really needed to provide the required resolution for this experiment to hunt for black hole at the center of the galaxy. And therefore, the largest mirrors in the world have in fact been active in this endeavor. W.M. Keck Observatory houses two of the largest diameter telescopes in the world, two 10-meter diameter telescopes. It is located on Mauna Kea in Hawaii. And the European Southern Observatory's very large telescope, which is located on Mount Paranal in Chile. It consists of 4 telescopes, each of 8.2 meter diameter. So these two really have been at the forefront of this exercise to trying to track down the central object in our galaxy. And a modern instrument which has been put together at the ESO VLT site sits underground under the 4 telescopes and brings light from all those 4 telescopes together to form an interferometer to provide an effective resolution of a 130 meter diameter telescope. So that is the best possible resolution that you can get by combining optical telescopes today. And this is called the gravity interferometer. Now let's take a look at the region that one is going to be studying. So this is a close-up picture of the region. The galactic center is somewhere over here. And at the galactic center, actually there is a highly variable source called Sagittarius A star, which produces emission in radio, infrared, and X-ray wavelengths, which can be seen. Faint, but can be seen. But if you look at this in optical light, this is how it looks like. It is just a black, dark region with huge amount of absorption by gas and dust that intervenes the galactic center and us. So visible light actually does not escape from here. So the only way one can study this using these telescopes that I mentioned is to go to infrared bands. It is not as though infrared has a very easy time to escape. Only about 10% of the infrared radiation can escape through this obscuring material. So one has to use that 10% escaping infrared band radiation to study the central object in our galaxy. So that's what is being done at both these observatories. There's another major problem. So if you want to obtain high resolution and you use a telescope with a large diameter, which gives you a milliarcsecond image, the atmosphere spoils it all. We all know that the stars twinkle. When we look up at the sky, we see that stars twinkle. The twinkling of the stars is due to the turbulence in the atmosphere. The refractive index of the atmosphere is constantly changing at any given spot. And what that causes is the image to dance around over an area of as much as 1 arcsecond or more. So therefore, if you take a long exposure image, your image is going to be averaged over that area, and you're never going to be able to get an image which is sharper than about 1 arcsecond. But what you're seeking is an image which is 1,000 times as sharp as that. So how does one get around it? What was shown in 1970s is that if you are able to image very, very fast, maybe 1/100th of a second or faster, then in each of these images, you actually get multiple spots, each of these spots being a diffraction limited image of the telescope, giving you the full resolution. But there are many, many such spots. There are a finite number. You can then take each of these images, put them on top of the other, and then stack them, and then produce an image which has a much better resolution. And since this image has to be taken very, very fast, it has got very short exposure, it gets very few photons. So you have to take many, many such images and make a suitable combination of these individual spots in all of these images. You need to capture hundreds of images per second and then analyze each of those images and then stack not just images, these spots in one image, but from all the images. So it is a highly computation intensive exercise, and this is called speckle imaging. And this is what has been employed both at the Keck telescope and at the Very Large Telescope in ESO through the 90s to create the high resolution image of the galactic center in infrared. And this is an example. This is the Keck telescope infrared speckle imaging of the galactic center. Once you process this image, you get an image like this, where you now see these individual stars. Here, this entire image size is 1 arcsecond on the side. So all of this would have looked like one blob if this speckle imaging was not done. So now these stars, one can then start following their position as a function of time and then try to see if there is any evidence of a very massive central object. Over the time, the 1990s went into 2000, a much more powerful technique came into being. So, and that is adaptive optics. Here, what one does is to actively sense and compensate for the wavefront distortions that are introduced by the atmosphere. So why is the image dancing around? That's because the atmosphere is turbulent. There is a plane wavefront which is incident on the atmosphere. Once it exits the atmosphere, the wavefront is curved. So this curved wavefront then produces a distorted image, and this distortion keeps changing with time. So therefore, you keep seeing an image which is distorted and time variable. So what one can do is devise a system by which this distortion is actually measured by a wavefront sensor, and that measurement is fed back into this mirror, which is deformable, and it is deformed into a conjugate shape so that the curved wavefront, which is incident on this mirror now, is now exits this mirror as a straight wavefront. So that way, one can correct for the atmospheric turbulence and get back a much sharper image. And this is what has brought a revolution in imaging through the turbulent Earth's atmosphere. Now, to do this correction, you need a bright reference, the image of which you use to measure the wavefront distortion. And this bright reference image can be created by shining a bright laser light into the sky and creating an artificial star. And that artificial star can be imaged along with the imaging region that you want to observe. And using that, one can get very fine image indeed. And here is an example of what happens when you switch on such a imaging system with adaptive optics. So what you saw before, this is without adaptive optics. And once adaptive optics is switched on, you can see the fantastic improvement in image resolution. So this then allows one to do the astrometry that we talked about in high precision, and also take light from each of these images and do spectroscopy, and therefore measure the radial velocities of all of these objects. And this adaptive optics technique has also been used both at the Keck telescope as well as the Very Large Telescope in ESO. So now, putting all that together, cluster the galactic center, and the positions of these stars can be measured over time, and their velocities too. And this is what the experiment reveals. The left one taken from ESO VLT, the right one from Keck telescope. And you can see over from 1995 to 2020, the orbits of various stars which have been measured. Of particular interest is this star, which is the smallest orbit among these, which now has been seen to go through the orbit more than once. This has an orbital period of 15 years. So that has the closest approach to the galactic center. I'll come to the observation of that in a second. So apart from that, there are almost 30 stars now for which near complete or partial orbits have been measured. And all of those orbits imply a concentrated central mass at the center of the galaxy of 4 million solar masses, coincident with the Sagittarius A star source. And that star, which was labeled S2, it passed through the closest approach to that central object on 19th of May 2018. And at that point, one could measure its velocity, and the velocity was 7,650 kilometers per second, which is more than 25 million kilometers per hour. And the approach that it had was within 20 billion kilometers of the center. And the analysis of this orbit told us that the mass included in this region is 4.10 plus or minus 0.03 million solar masses. And this is concentrated within a few hundred times the event horizon radius. Between then and now, there have been a couple of other stars which have been discovered, which are predicted to go through this closest approach in a few years from now. One of them has a 7-year period, and it will have the highest velocity at closest approach of 24,000 kilometers per second, and its closest approach would be 10 times closer than this star S2. So clearly, one is now able to pin the location of this concentration of mass down to a few times the event horizon. Can one go to very close to the event horizon? There is a difficulty doing so with stars of this kind, because if a star does approach extremely close to the event horizon, the tidal force of the black hole is going to strip it apart, and it is going to become just a blob of gas. So to go very close to the event horizon, one has to look at not stars but gas. And this has in fact been done. Gas clouds orbiting the black hole have been revealed during some outbursts by infrared imaging and spectroscopy. And from the measurements, it is clear that there is gas orbiting the black hole at an orbital radius about 1.17 times the event horizon. So now there is hardly any room for any other form of matter concentration of 4.1 million solar masses. So this definitely establishes the central object as a black hole and precisely measures its mass to be 4.1 million solar masses. And the measurements are so good now that one can now use this to test other predictions of general relativity. For example, the star S2, when it passed its closest approach, the velocity differed from what would have been predicted from Kepler's law by a certain amount. These dots are the measurements, and the red is the prediction of general relativity. So it follows exactly the general relativistic prediction. And the orbit itself, over time, would precess. In general relativity, there are no closed orbits. And just the beginning of that precession is also being detected now with the latest measurements. So now one is able to not only measure the mass of the black hole, establish that it is more or less within its event horizon, one is also able to use these measurements to test the general theory of relativity. So to summarize, profiling the central object of our galaxy has been an ongoing effort over the past 40 years. W.M. Keck Observatory and the ESO Very Large Telescope have been at the forefront of this exercise. Major technical advancements, infrared imaging and spectroscopy, speckle imaging, adaptive optics, optical interferometry, all of that had to be developed for us to reach this stage. And the groups led by Andrea Ghez and Reinhard Genzel have made full use of these technical developments. And this has enabled a precise measurement of the mass of the central compact object. The results now show 4 million solar masses confined within less than 1.2 times the event horizon radius. So there is very little room for any other form of object other than a black hole. And these new measurements can now be employed to test the predictions of the general theory of relativity. Thank you very much.
Great, thank you very much. That was an absolutely fantastic description of what happened, and shows why this work deserved the Nobel Prize so much. Thank you. So we have been looking at monitoring the YouTube channel for questions from the audience, and I hope both of you, both the speakers this evening, would be willing to take some questions from the audience.
Very happy to.
There is a place where the questions have been compiled. Samir, can I ask you to pick up some questions from the audience and ask it to the two experts?
Yes, of course. It will be my pleasure. In fact, it was a pleasure to hear both the talks. And now I'll just we have picked a few questions, so we can start. Since the talk by Professor Dipankar just ended, we could go to a talk relevant to his question relevant to his talk. Sri Swaraj Panchal wants to know how was the number, which is 4 million solar masses, arrived at for the black hole mass, I suppose, the central black hole.
Right. So you remember I showed an expression. So if you measure the size of an orbit and the period in the orbit, then using those two numbers from Kepler's laws, you can tell what is the central mass, what is the value of the central mass that is causing this object to go around in this orbit. So let's take the Earth. We know that the radius of the Earth's orbit is 1 astronomical unit, and the Earth is going around in its orbit 365 days. Using these two numbers, I can infer that the mass that the Earth is going around has a value of 1 solar mass. So that is the principle which has been applied also for this black hole measurement. I showed you a number of stars, some 30-40 stars for which orbit has been measured. And for each of them, you try to find what is the central value of the central mass it is going around. And all of them agree to a great extent, the value of 4.1 million solar mass. So therefore, there is a common central mass of 4.1 million solar mass around which all these objects are orbiting. I hope I have answered that question.
Okay. Yeah. So that's anyway. It was also covered in your talk a little bit. We are still waiting for any more questions relevant to your talk, but there is Arun Kumar who wants to just know the fact that what is the closest approach of our sun to the center of our galaxy, in case you know this number.
So our sun will more or less remain at about 8,000 parsecs. So that is about 24,000 light years from the center of the galaxy. So we're very, very far away.
At least. That's quite far away, thankfully.
Yeah.
By the way, the nearest black hole to the Earth is about 1,100 light years away, about 1,000 light years away.
That is correct. And
that is stellar mass black hole. Yeah, that we have found. So I know there are many people who don't sleep at night thinking the black holes are coming to get you because of all these movements. Very far away.
Yeah, that's not going to happen, thankfully. And you have the astrophysicists to blame for all this solace that you get, that there are no black holes coming to you. So we go on to some questions regarding the talk by Professor Sudipta and Mr. Mani Nair, I suppose. He's asking, can any massless object travel beyond the speed of light or through the speed of light?
If I may answer, so if we believe the theory of relativity and all the observations, experiments suggest the theory of relativity indeed is the law of nature, then you cannot. An answer is no. All physical particles which has non-zero rest mass, they travel at a speed less than the speed of light. Particles like photon, the quanta of light, which we call massless particles, they travel at a speed of light. They only travel at the speed of light. there are mathematical possibilities of hypothetical particle traveling more than the speed of light, but they are just mathematical. They are just probably black holes in 1930s. Okay, who knows? Physics always changes, but science is a thing which can change. But as far as we know today, no. The answer is no.
Okay. Another question regarding Hawking radiation, and Arun Kumar wants to know what it is.
Well, it is not easy to say what it is in a one-liner, but the simple answer is that whatever we have learned is what is called a classical black hole. What I mean is that we are only considering a theory without considering the quantum effects. But you can ask a question that what if I do quantum mechanics? Quantum mechanics is the laws which govern the properties of atoms and molecules. So you can ask an interesting question that what happens if I do quantum mechanics sitting very close to the black hole? And this is the exact questions which Hawking and his collaborators at that time asked in 1970s. It turns out if you follow the mathematical equations of quantum theory near a black hole, it gives you a spectacular prediction. It tells you that although the classical black holes are black, in a sense, nothing can come out there, quantum black holes are not really black. And they give you a radiation, and that radiation is exactly thermal in nature. The ideal calculations gives you thermal in nature. That radiation is a theoretical possibility again, because nobody has detected Hawking radiation, although there are certain analog systems where current experiments are going on, and there are claims that they have detected Hawking radiation for what is called a sonic black holes. So the Hawking radiation, in some sense, is a quantum radiation coming out of black holes.
And would you refer, since Professor Hawking was a very popular person and wrote a lot of popular literature, would you refer to anything that people could read about?
Yeah, I mean, Hawking radiation, there are many interesting blogs in internet, but just to say is that please understand that ultimate understanding of Hawking radiation requires mathematics of general relativity and quantum theory. I mean, without that, a proper understanding is impossible. But there are very interesting blogs one can look at. There are public talks by very good physicists, and those gives you a very good introduction to what is exactly going on.
Great. So I see one question which we can take as the last question before we go on. Just a moment. Yeah. So these are questions which are now at the extreme end and going into fantasy. So do multiverses exist, and are black holes ways to explore them? Any of you could take this one up.
Shomak, you want to take the bet? You're muted, I think.
I was expecting this question in the Ask an Astronomer because it's asked every year. How do we know? Actually, it's an interesting theory, but there is no way we can go outside our universe to know what's outside our universe, because so to some extent philosophically you can't say whether there are other universes outside our universe. But it's an interesting theory because it answers questions like, and this came from Hermann Bondi and others, even in the 1960s, 70s, they were saying, even if you ask questions like why is the value of light, speed of light what it is, or gravity what it is, and things like that, and then people started saying, okay, maybe there are many universes, and our universe has survived because the combination of various physical constants is like this. But there might be other universes in which these values are different. And so there are many universes, and so the multiverse theory in principle came. And then people started thinking about whether the multiverses can interact with each other. It's a very interesting book called The Mathematical Universe, which you can try and read about these theories. The question is whether we will ever know about these universes and whether there are any effects on our universe due to these other universes. And till now, we haven't come up with any such idea, in which case it doesn't really matter whether there are other universes or not, except for this theoretical nice idea that there must be other universes. But it's an interesting idea to pursue, because someday somebody might come up with ways. I mean, M theory, for example, or Randall and Sundaram's theory about how parallel universes might interact with each other and stuff like that. And so it's an interesting concept. Black holes going from one universe to another is something that's a very fancy thing that that science fiction has dealt with. I haven't seen anybody construct a black hole and wormhole connection that goes between universes. There are some very interesting papers on how to go from one place in space-time to another place in space-time within our universe to do that. But between universes, very few science fiction people even consider it. So, yeah, black holes maybe not yet. I mean, using black hole for time travel is also a very difficult thing to do, because as soon as I enter a black hole, I'm no longer myself. I'm torn into particles, so I don't come out the other end. That's always a problem. Excellent.
One more relevant question I think we can take is, you mentioned this image of the black hole in M87. So when can we expect an image of our Milky Way's black hole?
Yes, so that is very much is on the cards. People are trying to do that. But there is a very interesting problem with our black hole, although it is closer, is a scattering in the intergalactic medium, interstellar medium that exists between us and the galactic center. So this is being done at millimeter waves. And those waves do undergo scattering. Okay. And so scattering in the intervening medium broadens any image, so spoils your resolution.
And you showed in your talk how much of a depth there is in the plane of the galaxy to go to Sagittarius.
So that is the problem. So we have to see through the plane of our galaxy. There is a huge amount of scattering material, and this is causing a problem in the imaging resolution. People are trying to find ways to counter it.
Yeah.
And it's a very exciting methodology that is being developed. It's not fully there yet. But once that is done, I'm sure we will get one. But that is the current limitation. But maybe, who knows, in 2-3 years, perhaps.
But for the one that was published, M87, that happens because it is actually towards the pole of the galaxy.
Exactly. So we don't see through the galactic
M87, you don't have to go through so much of the galaxy, and so the scattering.
So that's a serendipitous thing.
No, it was chosen also because among all galaxies, it was specifically chosen because of this.
That's right. High galactic latitude.
Interesting to know. Yes, that's right. So one question which is making the rounds on the chat is, are there any to be explored for winning a future Nobel Prize in astrophysics?
I don't think you first set out to win a Nobel Prize and then decide your subject.
That's not very good.
Just to put a scientist's view of to this question.
But certainly the Event Horizon result is a fantastic result for a Nobel Prize of all the black hole related things that are going on now.
Mm-hmm. Sure. Okay. One last thing I would ask all of you to for is your comments on the significance of this particular Nobel Prize. What I'm asking is that we have a woman astronomer winning this prize, and one of the very few who have won it in physics, let alone astrophysics. So what are your comments, and what are your inspirational comments towards the students who are watching this?
I would say it is extremely welcome, and it also shows that gender sensitivity has become more common now, and we see it not just in the Nobel Prize, of course, but in other spheres of scientific endeavor. So the opportunities are becoming more and more equitably distributed. And I think it's a good time for women to not feel intimidated and start joining scientific pursuit.
Other comments? No? Okay. So with that, I think we come to the end of all the questions, relevant questions on YouTube, and to the end of this lovely session with three scientists who work on black holes, actually sharing their views with us and also telling us about the Nobel Prize, which was won last year by black hole scientists. Okay, so with this, we thank you everyone. Thank you all for being here on this late evening kind of a part of the show. Thanks to all the people who are here on live YouTube for being here with us since morning. Many of you are here since morning, and particularly the students who have supported us by giving really good comments about our programming here. So thank you all for being here and making this a really great success. Again, I'll remind you.
Thanks very much, Samir and Sonal and Ishan and the entire team, the SciPop team who's been working here, Atharva. Fantastic work. I think from 9:30 in the morning till now, we've had such a wonderful program attended by thousands of people. And so thank you very much.
Thank you, team. Thank you so much. And thanks to the audience as well.
Thanks a lot.
Thanks to the two speakers.
Thank you for your kind words. We'll ask all people who are here to again, the advertisement of subscribing the channel. You'll get notifications. There are several things lined up, not just this week, but in the in the coming future. So do subscribe. Do tell others that this is a channel to watch out for. All the recordings of today's sessions will be available for those who might have missed it today. They can just come back, rewind those sessions, and watch them again. So Sonal has stepped out, as Professor Shomuk has just told. The whole team has been working hard, and so with best wishes from all of us, let's end this day by again shouting out loud, Happy Science Day.
Happy Science Day.
Happy Science Day.
Happy Science Day for everyone. Thank you.
Thank you.
Bye-bye.
Bye.
Bye-bye. Thank you, everyone.